So, hi everyone. So, today, me and Rishi will present this paper, which is scanning physical interaction between behavior of 3D projects. So,
Getting the wrong screen on Zoom. Maybe. Okay. Uh,
okay. So, basically, now we kind of like start with physical laws and develop some numerical methods to solve the equations, for those kind of like real scenarios. By doing this, we can predict behavior purely from the fundamental laws, like those physical laws. So this approach has allowed us to create physically constant models um that like generalize those real world scenarios. But like, however, based on these laws, you have to assume you have like good accuracy and stability in your simulation, as well as like you need to have like all data. Oh, you need to have like all physical properties or meshes or data points available to define your system, which is kind of hard to have all that properties in a real world simulation. So right now we want get rid of like those complex phenomena, and like we want to easily capture certain behaviors, and we need a efficient real-time algorithm instead of like take bunch of hours or days for calculation. So we'll just like observe the behavior of like real project object, sorry. Um, so in that case, we'll bypass the need of like specific physical laws. Um, and we can capture like behaviors that which are like difficult to simulate, use those traditional methods. And we can also like run simulation in the real time. So today I'll basically focus on the scanning, which is the first part, and this part will be leave to Richard. So scanning is basically about like measurement. So before 2001, there's like some kind of like deformation models. They have like they do have like some haptic simulation like this one, and they also have like calisthenic techniques, which is um presented in the picture here. So the idea for this picture, um for this paper, um is like very far from simulating all the relevant information. So you can see like, so this just divide the space into A, B, C, D, E, or like some different spaces, and you have like a source of the sound, like which is S. You kind of like have all the reflections like here and here. So you just simulate those roots, and but yeah, like mentioned, it's really far from simulating all the relevant information, because like the real world scenarios is more complicated than that. So as for this paper, it just introduced a framework for exactly rendering haptic interactions in like complex virtual environments, but it still like doesn't efficiently handle like moving or deformable objects, and like interactions such as like grasping or pushing objects are not like that well supported, because um it's like dynamic. So this measurement system is quite important, because like for the paper we'll discuss today, we are heavily rely on this measurement system. So this one, it have several parts. So the task station is a like 3 BOF placement, which can just like rotate your objects in different positions. And this one is called FMS, which is like field measurement system. So it has like RGB camera and a microphone, and it's all like mounted on like 5 degrees of freedom positioning robot. So this allows us to capture visual and acoustic data, and also like for capturing like light field and sound field information. Yeah, this just gives us like realistic rendering and simulation in virtual environments. So as you can see, this paper is like this picture is like kind of like uh same person captured by 5 different like views from the same camera. Um, However, you can still notice like there's some inconsistency between each pictures, uh which is like due to the shadows or rapid movement or something like that. So we will kind of like use some classical techniques, like variable mask size loading. This helps smooth out noise by dynamically adjusting the mask size to refine depth selection. And we will use estimate on surface normal, which is like estimating the surface normal at each point. So we can enhance like depth consistency and reduce like errors or in curved or like in regular areas. Um, okay. So here we also have like force measurement system. We'll be discuss this one later. Okay, from this paper, we kind of like reconstruct the item from like a bunch of points, like 3D points, or to recreate the surface of the uh, object. So the principle behind this is like we automatically or manually set the Voxel grid size, and we map those 3D data points to the Voxel grid, and we so we create those triangular surfaces, and we remove outlier data points like the noise from the sensor. Um, we then like compute the surface normals for like smooth mesh generation. We also like run the Martin cubes algorithm to generate mesh. Um, then in the process of recreating the surface, we will like have some holes in the mesh And so we will later fill these holes to ensure the completeness. So finally, we'll remove isolated mesh components and optimize the overall data structures. So to ensure the consistency with the regional data.
I'll present the next part. So I guess like up until now we have like all of this measurement system that is calculating all of the forces that you can apply to the system. It was also getting you a multi-resolution textured mesh. But also like one thing I think is just that this kind of system was important because earlier what people used to do was um, at least the way I think about it was um, you had like some kind of fixed equations, and then you used some nice numerical methods to solve those equations, and then do your simulation in that way. Um, and this could be like any kind of simulation, and people always used to do that. And I think that's very powerful. It's very powerful even today. But like this paper came on, and what they said was, you don't need to do all this. All you need to do is get a lot of data, uh, and then just find out stuff from data. And in 2001, neural networks didn't work, or well, what it is called that time, connectionism didn't work, and and so they tried to get like so they tried to get like, all of this data, and then they tried to fit naive models on top of it. So at that time, there were a lot of iterative, like all of these Newton's method and all of these kind of things that came before neural networks or were popular before neural networks. So they used a lot of that. But like the main thing I think you should take from this paper is like setting the foundation for all of these neural methods and data-driven methods to actually work. So I think this paper does a very, very good job at making the case for just have a data-driven method, take a lot of data and and just make it work somehow. Uh, also, I guess like when I was at least like taking a look at this paper, one of the first things I thought is like they do like so much to like get to a multi-resolution textured mesh, and it's so hard to do that. They do like all of these steps. There's a lot of handcrafting in that. Particularly if you see this tiger example, in the paper they say that the tiger example didn't even scan properly. They had like a big hole in the bottom of the tiger, and then I'm assuming some grad student manually sat down and uh, fixed that hole. So you might think like, why do you need to do all of this? Uh, well, today there are nerfs and Gaussian flats and all of that, but there wasn't any of that at that time. You need a multi-resolution textured mesh back in 2001. Um, there were still some people trying to do point-based methods, but it was very, very hard to do all of that. So maybe like that makes it at least like one of the at least makes it clear like one of the questions that I had when I was trying to read through this paper for the first time. Uh, but yeah, now you have like all of these measurements, and then you now want to focus on like how do you get the physical interaction behavior from all of these measurements somehow. Um, so the goal is you do all of these measurements, and then later I'll do some new kinds of simulations. So I'll probably like I probably in my computer now I have like this tiger over here, and I want to say what will happen if I push it, or what will happen if I pull it somehow, or what happens if I drop it to the floor. So I want to do those kind of simulations after I finish taking these measurements. So so that is kind of like the goal that they try to do with this. And for the most part, the paper divided this into like multiple phases. So one was deformation modeling. Uh, The other one was contact texture and friction. Uh, if you kind of remember about IPC methods or log barriers, that wasn't there in 2001 as well. So yeah, it's like super old. Uh, One of the first papers that did like this data-driven stuff. And then they also modeled sound because they also wanted to simulate sound. So, but yeah, let's start by talking about deformation. And so assume you have like some body and it has some domain omega here, and then you also have some boundaries of the body well defined. And why do you have like the boundaries well defined? Because it's a textured mesh. It's not any of the recent representations.
After it's projected, or that the boundaries of surface is on.
So
Is this after it's projected, or is it still
is this after what?
after you project?
Oh yeah,
Or
yeah.
is it?
No, this is like before you project it to the image plane. So assume you have like all of this in like some body coordinates. Uh, you already converted from world coordinates to body coordinates, and now you have this all of this in the body space. Uh, and Doing it to the image space, I think, is a different problem because and this paper doesn't even tackle it. So this paper just tackles physics-based animation or simulation. And then how do you go from the simulation to the image plane or the rendering part? This paper doesn't talk anything about that. You use whatever approaches you have to do that. But yeah, you first start out.
So what the problem actually, so it is the paper trying to, the paper is trying to simulate how bodies behave through data, like that's the problem.
Yes.
Okay, the fine problem, that's permission.
Um, so, but like the reason we still have all of these models is because you want to take some data and fit a model to it. So
Okay.
later you can do some new simulations.
Okay. So other than calculating this stuff like boundary stuff, you said it's just like 3D stuff that is it coming from 3D images, or is it like based on like 3D images they like they already object, then they calculate this boundary stuff. Or is it just calculating from the images?
Yes. So they had a reconstruction process. So they do all of these reconstruction process that he briefly talked about. But at the end of this reconstruction process, you get like this mesh, right? So if you have a mesh, then you can find out the boundary of the mesh.
Oh, approximate.
Yeah, and they use like a bunch of things to like complete this reconstruction process. So uh, yeah. Okay, so now you have like the object and the boundary. So you start with Hooke's law, but it doesn't quite work for 3D. So, or well, it doesn't quite work for having body forces and all of this elasticity. So some effects. So just quite works for like 1D spring. So you just generalize Hooke's law. So you have like the Navier equations. Uh, Essentially, the way you should think about this is without like exactly showing how these Navier equations come about. Let's just take these Navier equations for a minute. And on the right, you have like this BI thing. And what that is just your body forces. So, so that is all your external forces. So this could be stuff like gravity, or it could be if you probably push it somehow, that would be a external body force. Uh, but for now, let's just say that it's all of these external body forces that apply on the entire object at once.
Yeah.
So the easiest example is gravity, but maybe you have something else, wind or whatever. Then you have this linear elasticity operator. And over here, the main thing you should take a look at is you have this new term or V term over here, which is the Poisson ratio. and and you have like this 1 minus 1 by 1 1 by 1 minus 2 mu term, which is important because the maximum value of mu you can get to is 0.5. So you can just think what would happen if it would 0.5, uh it would get to like a very, very high value. Um, le- and then you have like this G force over this G over here, which is your shear modulus. So so the way you should probably think of this is let's try to rewrite this a bit more simply, and you get this. Um, so you have like this X, which should be satisfied on all of the domain of this. So it should be satisfied. So all your Navier equations should be satisfied over the entire omega in the entire domain. And you have some second order differential operator NU over here, which is which essentially makes this into something that looks very close to like a finite element PDE that you finally want to solve. And most of these methods, like finite element method, end up with like very, very similar PDEs that you end up wanting to solve. And usually you'll also have like on this thing that on the image I say on the image they say is tau p. You have like all of this boundary as well, right? So all of these boundaries will just be specified by Dirichlet boundary conditions in this case. Um, and maybe like this is quite a while ago because people don't often do this. But are you familiar with Dirichlet boundary conditions? Okay, so just like probably think of it as you have some you have a PDE. Let's take like the simplest example. Um, and this is some second order differential operator. But just to make it all simple, let's say this is the Laplace operator. Then you have your omega, the domain, uh, take on all of Rn, for example, with this PDE. Then your then the most popular kind of conditions could be you could you could you could probably have uh, you could probably have y equals fx, where f is some function, or y or something on like the or something on like nabla y. So this is like the Dirichlet boundary conditions, and this is the Newman boundary conditions. So just like have some content, have like y parameterized by some function, f, some random function, or like nabla y be parameterized by some random function. And the upper one would just be your Dirichlet boundary conditions. Okay. So okay, now that you have all of this, uh, I so the paper kind of starts with this uh, uh, the Navier equations, and then it directly gets to the answer in a very, very non-intuitive way, which wasn't quite clear to me the first time I was reading the paper. So let's probably try to think about this very differently from or differently from what they do in the paper, but get to a similar outcome, the exact same outcome actually. So so the main thing you should be thinking of is you have your G, but let's just think of that as a constant. But then you have the nabla square U, which is important because all of that is like some of your prescribed motion that you have for the object. Um, and then another important part is that you have this P thing, and the P is just all of your applied forces on the object. So mainly you want to solve for U and P, the prescribed motion and the applied forces. And any of the solutions that you get, like the Navier-Stokes, you want like both of these, you want to solve for both of these terms. And then you try to find out a few tricks. So So the first trick is you say that the body force is a point force. So any of the external forces you're getting would all, or in this case, would be applied on like a particular point. Um, so what you can do is just like take the body force and replace it with a delta function. So now you just have like this. Uh, so now you just have this delta function, which, if you remember, looks approximately looks something like at, at one point it is pretty high, and based on the things that you pass in the delta function would look something like this, or look something like this, or whatever you pass in the delta function. But eventually, just like have a point force. Uh, the, uh, then another thing you should notice is you can also exploit linearity in this, and I'll try to go over this because uh, just because most of this needs like uh, some or most of this needs a lot more time to go over. But essentially, the main insight comes over here. After the first insight that you make the body force be a point force, then the main insight is you exploit linearity and then solve this in the Fourier space. Um, and the way you should just think of this without like trying to understand this fully, if you understand the previous things like the Navier equations, just for the Fourier transform, think of it as like all the nabla squares become minus gi squares, and uh, and you have all of these nabla of nabla something terms, and those will just become minus gi gz. Um, and then you want to solve all of this in the Fourier space. But another thing is, so you're doing all of this effort to solve these Navier equations to make Green's functions. Um, and uh, okay, let's put it this way. Like maybe like the way you should probably think of this is you want like some of these Green's functions for which what you'll do is, or what they would represent is, assume you have an infinite elastic medium, and then you do some kind of point force on it. How does the entire medium change? So, because a point force doesn't only change one part of the body, it changes everything. So, if you do a point force on, let's say, some part of the object, how should rest of the object deform according to it? Uh, so Green's functions intuitively just allow you to represent that somehow. So that is what you want to get like for that is what you want to end up getting for with like all of this stuff that we are doing with Navier's equations. Get like some kind of basis or some kind of Green's functions where you want to solve this. So again, we'll not go over how to solve this, but the main thing you should take a look at. Sorry. Uh, well, no, because the solutions to the Green's functions won't be unique because, like in the entire system, your measurements will also change. The measurements are not always going to give you guaranteed stuff.
Given that Green's function is the only way to solve it.
No, that's not. Uh, but you should just try to think of this as you have like this first term, which is allowing you to have some kind of uniform radial deformation, because just think of it as like the Poisson ratio is telling you like how much lateral deformation you would have. So the first term just allows you to get like some kind of uniform radial deformation. Then you have the second term, which is like some direction dependent response. So based on like the direction of where you do, uh, based on the direction of where you apply the point force. And you also have like this one by R term in the isotropic expansion. Uh, and And that's because the elastic energy would just dissipate across the object, as in how you go farther away from farther away from where you have put applied the force. And if you just think of like this term in the bracket, you also have a singularity at r equals 0, right? Which you'd expect, because that's the place where you're applying the force at r equals 0. And as promised earlier, you have fundamental solutions satisfying the Green's functions. You have one for u and you have one for p. So think of the solutions as you want to find how displacement decays with distance from the point force that you apply. Uh, and then you have one for u and one for p, as we were talking about earlier. You can actually like also write this as a sequence of spherical harmonics, uh, but but we but we won't quite talk about that. And essentially, all you want to say is that any of the deformation that you can do in the object, it can be just represented as a linear combination of all of these responses that you get from solving the Green's function, from getting like some fundamental solution satisfying the Green's function. So, uh, so, so, uh, so now you have like a decent way to like model how the uh, or now you have a decent way to model how like all of the displacement decays from the point force. Uh, there's also a bunch of integration techniques that you need to do next to make it work for the entire volume. But let's directly see the solution for this. Uh, the main insight that comes over here is uh, what you want to do is like you think you have like this circular boundary for the object for a minute, and you want to uh, and you want to just like discretize the boundary into all of these small pieces, and then you will do some kind of approximations for the u and p, the traction, and for the u and p solutions that we got earlier, and then we should be able to like make this work for the entire volume instead of like individual points. And uh, let us bring all of this together. Uh, but you should think of like you should think of like this making a system of equations. Your system of equations would essentially look like this. So the system matrix would have a lot of off-diagonal influence coefficients, and all the coefficients for this matrix on the diagonal would be all your jump terms and double layer potential terms. And and the influence matrix would just like have all of the single layer potential uh, terms. But uh, we skipped quite a few steps while trying to get to this. But does this look familiar? Uh, HU equals GP. Does this look like a familiar form of something? It's just a system of equations. So what you can do next is just just think of this as the system of equations. You have some unknowns that you want to solve. Uh, and back in that time, there weren't a lot of, well, there were quite a few ways to solve system of equations. They ended up using something which is quite long forgotten, Sherman, Morrison, Woodbury, to solve this. It's just like this. It just used to be very, very popular before people stopped using all of this, these kind of system of equation solvers. Now everyone just is gradient descent for everything. But yeah, at that time, like it's also easier to do with this because like because you often do gradient descent when the Hessian is not given or when it's like really compute intensive to calculate the Hessian. Well, but essentially, they just solve this system of equations with Sherman, Morrison, Woodbury. And yeah, let's like get back to capturing for a minute. And uh, Yeah, so now you apply like some kind of control force. You have this robot arm that does that, and the surface deformation is measured visually using like the stereo vision system that you have. And then you calculate the range from stereo and segment the image into object surface and other things based on the geometric model of the undeformed object. And then you would also like use some kind of optical flow to calculate how much it's moving. So like in this case, you have the undeformed object and you know how much it's moving given a force because you did like optical flow calculations. Uh, so the vision system would do all of this and map whatever deformation you have onto the mesh vertices. So because like all of the things that we did was we assumed that it's a volume, but but what we need to actually do the simulation is we have a mesh with multiple vertices, multiple faces. And then you need to say, how do you move the mesh faces and mesh vertices? Um, so you know how to move the volume, but well, how do you move the mesh now? Um, so you also need to find some way to like change all of this volume deformation into what happens when you deform the mesh. And how do you change the mesh vertices individually? And all of this visual system just helps you do that. And same for this. We already have some displacement field, and you have force for all of the vertices of the meshes now. And you will already like estimate the Green's functions by relating the displacement field to the applied tractions. Uh, and if you're thinking like, how do we get tractions? By the way, you only calculated forces. Well, you just take like the force and divide it by the area that was on the robot arm, and then you get like the traction. Um, uh, so so now you end up with like this system of equations with um, and now you want to get back to like all of the volume stuff that we were talking about. But now I want to ask you again, does this look familiar? And it's the same thing. It's a system of equations with a few unknowns. The
Also, we just try to compute small u, right? Or each. Okay, what are we trying to do? What's the value you want to get?
oh so
Well, what's the value, well, which value you want to get in this?
oh yeah so you want like all of the uh, so, so well the assume you have the u for now, the capital U for now.
Okay.
Some of the U's won't quite be observed because the volume is continuous and the measures will not continuous. So some of the U's won't be observed, but assume you have the U for now. And assume that you also have like the tractions. So you have the small U's as well.
Sure,
And
so-
then you just want to solve for like the P matrix.
Okay.
So yeah, you again do a similar stuff. As earlier, you solve a system of equations. Uh, And once you do that, you will get back to like this system of equations that we talked about earlier for volumes. And you can already solve this with Sherman, Morrison, Woodbury, like this they did. There's like all of this stuff about interpolating across resolutions, interpolating across missing values. And you need all of this because you have like unobserved elements of the capital U. Because essentially you are solving like nabla square capital U is 0 with the Dirichlet boundary conditions with known values. So you have a bunch of unobserved things that you get in capital U. So to do this correctly and just solve it for like all the p's, what they end up doing is you had like this you had this thing which didn't quite seem useful at the time, the having a multi-resolution mesh instead of just one mesh. And this is where this comes into play. So they use like multiple resolutions of the mesh to interpolate across hues. So all of the missing values of hue that you did not observe, they'll just interpolate across those values so to make like a solvable system of equations. So now we talked about deformation. Now you can measure a few things in deformation. You can deform it however you want and you can simulate it well. you can change the mesh and simulate it well. So the next thing was contact texture, uh, uh, which is like all of this friction and all of this stuff. So so if you have tried to do all of this physics-based animation, there are a lot of friction models out there, and they use a very non-typical friction model for this. Non-typical even for the times of 2001. Um, uh, or at least what I think is non-typical. I didn't know much about the field at that time. I don't know much about how the field was at that time. So uh, it seems like this is a very non-typical model of friction. But yeah, let's start by talking about this. You have this mu e term, which is like the coefficient of friction that varies across the entire object. Um, because like the entire object might not have the same coefficient of friction. And then you actually have the friction calculation. The friction calculation is simple. You take the coefficient of friction, multiply it with the normal forces, and then you also have like this direction where the friction is applied. So what they end up doing is model all of these variations in coefficient of friction as an autoregressive process. So so the way you should think about this is all of this is an autoregressive process now. So you have like this k term, which is how many times do you do this autoregressive process. Usually, the more you do, the more accurate it would be. Then you have some kind of noise here. Uh, so you have like this noise that you would add, and then you also have like this autoregressive coefficients that you will apply to all of the things that you have seen previously to get like the current friction. So so that is essentially what you want to end up doing. But the way you should, I think like this is not. I don't like this way of thinking about it. The way I like to think about this is like you think about like this AR process. The previous slide was an AR process of like any index, but like this is an AR process of an AR2 process. The paper also ends up using an AR2 process. But you think of you, but it, I think it's better to think of this AR2 process as like a first order Markov process. So essentially, write this in state space coordinates, which makes it a bit easier to understand this. And just think of this entire process as now a stochastic process, and think of what you would get if you would like apply Fokker-Planck to this. You would get like essentially end up getting like this diffusion term and this drift term, and I think that makes it like a bit more intuitive to see how this autoregressive process works. Okay, so let's talk about measurement, because you don't quite have the friction directly. You have like this thing that moves across the object, but that doesn't quite get you the friction. So so first what you need to do is you need to plan where and how you want to rub the object across to get like all the contact texture. And you already have the surface normal. Um, so if you know the surface normal, this should be an easy problem. But it turns out the approximation is not good enough, even if you know like where the surface normal is pointing out from.
What's the friction period? Like, is it like a friction that you can, if you touch the objects, like the surface, is it friction between the surface? You touching the object with it inner, like any inner frictions. What's the friction period?
Yeah, exactly. So it's like the friction between this robotic arm and the object itself. Uh, so what they essentially end up doing, because like the surface normal way of like estimating the friction was, they say that it's like very noisy, and it turns out like it's not, does not give you such good values. So what they end up doing is like they choose like a certain patch where they want to run their robot arm, and what they do is like they calculate this F plus friction and F minus friction. So like you stroke it in one way, then you stroke it in another way. And then you get like this F plus and F minus friction. And then you just use them to say, oh, your surface normal is this because you calculated like force this way and this way. So, and then what they do is they use this surface normal from the measurement, uh, and then they actually get the friction. So, uh, so you get like the mu e term, like the coefficient of friction, by solving for every point and the autoregressive process that we were talking about. Uh, so, so there is a few minor things over here. Uh, Also, when we talk about rendering here, um, it's not quite same as what like Alex was asking earlier. But but to actually render this in the sense that you want to do it for the entire object, it's a bit harder because you have like all of these triangles, and you only have like what they have on the vertices for all of these values. So what they end up doing is first, if you want to like get some like so first what you do is you take like multiple observations, and then say the green one is the one that you want to estimate for. So first you end up doing some barycentric interpolation, and then you also have like your autoregressive process that allows you to get the coefficient of friction. So they just do some discretization of this autoregressive models, and then some interpolation. And finally, with all of this interpolation that you do, you end up getting like the effective friction for any point pretty accurately. And another thing is you might think like there's also like a lot of steps that you do after like getting the friction. And essentially, the paper doesn't give any methods to do that. They say that after you get the friction first, after you get the coefficient of friction, all you use is like the standard methods that used to exist. Um, so there were a bunch of standard methods at that time, and the paper uses something which we probably don't need to talk about. But the paper uses something called Ghost, which is a closed source system. We don't know what it does, but essentially they use it to create like all the simulations. But essentially, just think of it as you already have the main parts, friction coefficient, and you pass it into any kind of method that is used to handle all of these frictions. They use a very they use a method that used to work very well at that time. You can use whatever you want from once you get like the main parts of this. And then you have like and then they also did sound, which we can like briefly go past, or maybe like we can like go right past this because we're already out of time. So uh essentially they do the same thing, like a brief overview of the main thing that you should get back from this is you measure the sound at multiple places. What you then do is try to somehow identify what part of the object creates what kind of sounds. Then you try to match those with a predefined resonator bank that you have. So they have a bunch of different frequencies of sounds predefined. You say that this part of the object is giving you these kinds of sounds. And then you have that for multiple parts of the object through the measurement and that process. Then during simulation, what you end up doing is you say, oh, I poked it this way. What all parts of the object are influencing the sound at this point? So then you say, oh, these two parts of the objects are influencing the sound at this point. And then they have some kind of impulse response stuff that they do to combine both of those sounds, essentially do like a simulation and combine both of those sounds to get like finally what you would get. So similar in spirit to what they were doing for deformation modeling. But we won't go through details of this. You can uh, I don't think the paper also like the paper. I think like the paper explains this a bit non-intuitively, but maybe like you can take a look at the paper for this. Um, and they have like some really interesting videos that they show. Uh, so uh, maybe like it's worth taking a look at the videos they have. So maybe like I can move past. Oh, uh, okay. I don't know what happened, uh, but I think like there's this video which was very interesting. Oh, okay. Okay, that's the next one. Yeah, this video which is really interesting. And what they do is uh, like the other videos were just demonstrations of how of the simulation, but in this what they do is they synthesize some sounds and then they show real sounds, and you have to try and guess which one is which I thought was very interesting because like they show that you can produce really accurate sounds from this. Well, I guess like the projector sound is not working, so never mind. Wait, or wait, maybe it is. Yeah, so they played like two of these sounds and they highlighted which one was synthesized in real, and it's actually surprising how accurate the kind of measurements they do are, especially for a time which was a long time ago. So yeah, that's about the people.